Hello, everyone. Come on in. Anybody have any questions before we get started? Nada. All right. Make sure you check. I moved some of the dates back. Like I think chapter 30 concept questions I might have moved back. Chapter 31 should probably do I think I set them both to Monday and Wednesday. So concept questions are probably due Monday, but check for yourself because I'm going out of memory. So there's a good chance all this is wrong. But do check in my lab and mastering on your homework due dates for chapters, not 29, we finished that some time ago, but chapter 30, 31. After this, we're going to the chapters on thermodynamics. And then after that, we'll go to the chapters on quantum mechanics. So that's our plan. Anybody have any questions on anything before we get cracking? All right, well, this is chapter 31. It's called Maxwell's Equations and Electromagnetic Waves. And this is sort of the linchpin chapter in the sense that it brings all this back together. So we've looked at Gauss's law, we've looked at Ampere's law, we looked at the Biot-Savart, which was a way of calculating the magnetic field that was a little bit more complicated, but more general than Ampere's law. And we looked at Faraday's law. There's a problem though, we were sort of missing something that Maxwell discovered, and we're going to, of course, address that today. And there's another law. There's actually 4 equations that Maxwell introduced us to, and we haven't given that last one yet. So something sort of equivalent to Gauss's law, but for the magnetic field. It turns out from a study of vector calculus, which, as I told you before, was co-invented by Oliver Heaviside in Great Britain, and I think his first name is Stephen Gibbs. I think his first name is Stephen, but it's Gibbs, an American, where we got Gibbs free energy from. They independently both sort of created vector calculus, and it was mainly Oliver Heaviside who drummed up support from Maxwell, because Maxwell basically took all the work of Michael Faraday and all the other people, but Michael Faraday was probably the one that did the most, even though he was the least mathematically prepared to do what needed to be done, but the most competent experimentalist probably ever. So he just literally could take Faraday's work and translate it to mathematics. Well, he did that, but he did it with quaternions, which is unfortunate. And he also did it with some potentials that we don't use anymore, and he made it pretty obscure. It was hard to follow, but Oliver Heaviside comes along, and he's one of the what historians have called the Maxwellians, and he basically turns Maxwell's equations into vector calculus form that we know them today. And there's 4 equations, and it turns out that under vector calculus, to completely describe a vector field, you only need its curl and its divergence. That will determine a vector field up to a constant, and that's really all you need. You can always add a constant to a vector, and it's not going to make any big difference, or almost always. So anyways, the curl and the divergence is all you need. When you see a closed integral E dot dl, there's basically something we call a generalized Green's theorem, which is basically saying that there's a integral relationship that relates to how much is in a container versus how much is leaving it and stuff like that. So whenever we look at that, there's some kind of relationship between it, and you can quickly convert it. I'm going to put you on hold a second. I got a call that I don't normally get, so I want to make sure this is okay. So hold on just a second. Hello. Sorry, everyone. That was my former wife calling about my daughter, who I'm trying to find right now, and I was kind of worried about it. And she called me out of the blue, so that just wanted to make sure everything's okay. Everything's fine as far as we know. I just don't know where my daughter is. So, anyways, so that generalized Green's theorem, Stokes theorem type thing basically says that the amount of stuff that leaves a closed volume has to have went through its outer surface. That's one version of it, right? And that can convert that closed integral of E dot dA into a divergence. And then that closed integral of E dot dL, that's another version, and that can convert to a curl. So you can actually get a differential form for Maxwell's equations, which is what you normally work in more advanced classes as opposed to the integral form. And your book does it in the appendix in the back. So you can definitely check those out. In general, they're really beautiful symmetric equations. I usually have a coffee mug or something with them on there, but I don't have it with me right now, so I'm not going to show it to you. So that's what we're going to do. And the first thing I'm going to do is discuss with you basically what's wrong with Ampere's law. So let me turn on my document cam and show you what's wrong with Ampere's law. Or let me just stand here and look dumb because I didn't hit the right button. Yeah, that works pretty good too. Okay, so Ampere's law says the closed integral of B dot dL is equal to mu 0 I enclosed. And we usually will drop that enclosed part, and we'll do that later on. But the nature of this thing is that this side right here is a line integral around any closed line. Okay. And then what it's equivalent to is this side, which says basically mu 0 times any current penetrating the surface that is bound by this curve. So for instance, if you think of a wire like this, and you think of the curve like this, then you might think this side right here is any current penetrating this surface, as if you just took this ring here and laid it in a mixture of water, dish detergent, and a little bit of glycerin. You know, you'd pull it off and it'd make basically a bubble surface. You know, that's how you actually make bubbles like you used to blow when you were a kid. Well, it turns out the nature of this is any surface spanned by that thing, or say demarcated as an edge to any surface, any surface that has its edge defined by this circle here is sufficient. So in fact, we could actually consider sort of a surface like this that looks like I don't know, a net or something like that. So that surface is valid too, which there's no big deal here. I mean, a current going in is obviously going to go through that surface or that surface, but the real thing is this is true for all surfaces that span this shape. So if you think about another case, you might actually think or come up with something a little more clear. And the other case that we're thinking of, or that I'm trying to get you to think of, is this one, where I might have some charge going in this way. And of course, that's going to make a parallel plate capacitor. But you could say, well, wait a second, what about if I use the integral of B dot dL as the integral around this surface, then or around this circuit, then this surface would be fine, but so would this surface. Right, so that surface would also be okay. And there's no actual current going through here. All we actually have is an electric field. And of course, the more current comes in here, the stronger that electric field has. So we've got something that we know has to be equal to the integral of b dot dl on the left-hand side. But if I use this surface right here, I've got no I enclosed. So what Maxwell sort of did was consider a very special case. So let's do that. Let's consider a special case, see what we get, and then see if that makes any sense, and if that's actually the generic response. And in fact, it will be. So let's look at this. We're going to say probably that inside here is an electric field, and we already have that the closed integral of E dot dl is equal to negative d phi b over dt. That, of course, is Faraday's law, which also happens to have the magnetic flux in it, and Lenz's law, which tells us basically that a changing electric flux will create a current. So we have this law, and right now these two are not very symmetric equations. This one looks uniquely different from this one, or distinctly different, I should say, from this one. So we might be thinking maybe this term over here actually needs something with a derivative in it or something along those lines. So what we're going to do is try to talk about what could that actual term be. And this is sort of, like I said, what Maxwell did. What we know is I is a dq dt. So we want something that sort of looks like a dq dt, because a mu zero times something with the units of dq dt is what is feeding this. So our thing has to have units of mu zero times something dq dt. So if we think about the capacitor over here, we might say, well, Q is equal to the capacitance times the voltage. And the capacitance, of course, for a typical capacitor is epsilon 0 A over D. And then in addition to that, the electric field is, the voltage is the electric field multiplied by the distance d. So if the separation here is d and the surface area here is A, then this is Q, which equals the capacitance times the voltage. So when we do that, we actually have something that looks like a current or like a charge. So now we might want to consider what is the actual derivative of it. So we'll say, okay, what about dq dt then? Because dq dt, if I put a mu zero in front of that, I'll have something with the right units for what goes on the right-hand side. So if I take the derivative of this, I'm going to get an epsilon 0. Notice these d's cancel out. And I'll get an A times dE dt. And that may or may not be it. But if we remember the symmetry of this one, we actually talked about a magnetic flux. And we actually know of an electric flux. So maybe the derivative should be a derivative of the electric flux as opposed to epsilon 0 A times the derivative of E with respect to T. A more general and symmetric version would be epsilon 0 D phi B, or phi E, excuse me, over dt. If we try that, well, we'll clearly have the right units, and we would make the conclusion that the closed integral of b dot dl is no longer just mu 0 I enclosed. We could put a mu 0 in front of this, and we get mu 0, this is plus, epsilon 0 d phi E over dt. And it turns out this was for the special case of this little capacitor, just like before when I calculated the energy per unit volume, you know, that little energy, we got 1/2 epsilon 0 E squared for a capacitor, and we got 1/2 B squared over mu 0 for a solenoid. Those turned out to be the general true expressions, period. Well, the same thing just happened here. This turns out to be the general true expression, period. And in fact, all we need to do is find a changing electric flux creating a magnetic field when there's no current about. And lo and behold, that was done. And once that was done, that confirmed experimentally what Maxwell had predicted. And in fact, it goes into actually creating a wave equation which Maxwell was able to come up with as well. And because of that wave equation, that detected, that showed we should be able to detect a changing electric field causing a magnet, or a changing electric flux causing a magnetic field, and a changing magnetic flux causing an electric field. And that should actually propagate out over space. And it turns out that Heinrich Hertz found that. Other people were looking at it. Heaviside was looking at it. The other Maxwellians were looking for it. And actually, they had done experiments that seemed to suggest they already found it. They just hadn't recognized it yet. But Hertz, who was working under Helmholtz, in fact, did find it and recognized it when he found it. So this is now the true version of Ampere's law. And often we call this term right here the displacement current. But that terminology and everything is not that helpful because it was based on an idea that never panned out to be true. But they would call it I sub D either way. So you might hear displacement current come up from time to time. And basically it'd just be mu zero times I plus ID. And in fact, your book makes the point that, in fact, there's another term that could be put on here. If there's a material present that actually could create or contain a magnetic field, you'd actually have another term in here. But you could also fulfill that by replacing the mu zero with just a plain mu for the material that you're dealing with. Similarly, if you're in a dielectric, you can also replace this epsilon zero with epsilon. And of course, epsilon is equal to some kappa times epsilon zero. So that would work as well. So you can use mu instead of, or excuse me, mu instead of mu zero, and you can use epsilon instead of epsilon zero in the case of materials being present. Okay, a more advanced course would show you that. The main thing is we needed that extra term so that we can then, of course, state Maxwell's equations correctly. So let's look at an example of this. Okay, and this example is more or less like the one, example 31-1 in your textbook. But basically, we're going to say we have a 50.0 picofarad air gap capacitor. And air gap just means epsilon is essentially equal to epsilon zero. Okay, and it has a equal to 100 square centimeters is the surface area, and it's charged by a 100-volt battery. And I'm going to put a dot here too, so I can treat that as 3 sig figs. Okay, what I want to do with this is I want to calculate the current into the plates. At t equals 0. B, I want to calculate the let's say the rate of change of the electric field. I want to calculate dE dt at t equals 0 as well. And C, let's say we calculate the magnetic field induced. Okay. So first off, we know C equals Q over V, which means that we can figure out more or less what's going on with this by treating our typical circuit that we did earlier, which is basically us just charging up a capacitor. And when we charged up a capacitor, what we found was that Q is actually equal to C times V0 times 1 minus E to the negative T over RC. So that was our original value of, or excuse me, that's our function of Q as a function of time, because basically it's going to exponentially grow up to reach asymptotically the C times V0, which is basically the same charge it would have if there was only a capacitor and a battery in the circuit. We're using a 100-volt battery, we're using a 50 picofarad capacitor, and we're ignoring the resistance basically. So what we want to figure out is the current into the plates. So let's look at I. Well, I is equal to dq dt. And of course, dq dt, if you want to do this, you can say d by dt of, well, let's do it this way. Let's pull the constants out in front so it looks a little less confusing. I'll do C times V0 times d by dt of 1 minus e to the negative t over RC. Then immediately you see that this first one term is not going to give me a derivative at all. It's going to give me a derivative equal to 0. So I get C times V0. And then the derivative of e to the negative t RC is e to the negative t over RC. But now I got to take the derivative of what's up here, which is negative 1 over RC. And it already had a negative, so I'm just going to say over RC like this, and that took care of the sign. So I ultimately get just plain V0 over R, which is 100 volts over R. Oh, I did mention that, didn't I? Oh yeah, the resistance was supposed to be given. Sorry about that. Let's say resistance is equal to, I don't know, let's say resistance is equal to 2.0 ohms. That'll work. And I'll say it's 3 sig figs, so we can still get 3 sig figs. So that's just 50.0 amps is what that comes out to be. So that's a pretty big amperage for part A, but we now have an answer, so that's helpful. Anybody have any questions on that part? Now, part B, I want to know what the changing electric field is as a function of time. So for part B, I'm going to realize that the electric field inside a capacitor, E, is just sigma over epsilon naught. Remember, when we used Gauss's law for an infinite plane, we found that it was sigma over 2 epsilon naught. But when you take an infinite positively charged plane here and an infinitely large negatively charged plane here, they're both tending to pull a positive charge this way. So those two magnitudes add up to give us sigma over epsilon naught. But sigma over epsilon naught is just the charge per unit area. So I can say Q over epsilon 0 times A. And that should actually give me the electric field. If I want to know the instantaneous rate of change of the electric field, which is what I'm really looking for, that's dE dt. It's got to be 1 over epsilon 0 A times dq dt, which of course is our current again. So when I do that, I can say this will be 50.0 amps for the dq dt over epsilon 0, which is 8.85 times 10 to the negative 12th. And remember, that actually had units of coulombs squared per Newton meters squared, which you could also do in terms of volts and stuff, but either way, it's good enough. And then the area is 100, and then that's centimeters squared. So I have to say times 100 centimeters is equal to 1 meter, but I got to square that to make it work to the proper number because it's centimeters times centimeters. When I do that, it might be nice to have a calculator, which I do not seem to see anywhere. Okay, so anybody want to attempt to do that calculation for me? Anybody have an answer? All right, I'm gonna try my phone calculator, which is just prone to errors. The buttons don't always hit when I mean to hit them. So I'm going to say 8.85 e to the negative 12. And multiply that by 100. Actually, I'll take 100. And I'm going to take 100 times 100. And divide that 100 by it. So I divided 100 by 10,000. I got 0.01. I'm going to multiply that by 8.85. That's my denominator. And now I'm going to divide 50 by that. And I got 5.65 is 5.65. So those are extra sig figs that I just put here, times 10 to the 14th. And that should be volts per meter per second, basically.
I got the same number, but not the same exponent.
Okay. Let's see. I'm going to do.
I got the same exponent and the same number.
Okay, let me double check. If I get another confirmation of that, then I'll trust our work and we'll see what happened with his. So 8.85 10 to the negative 12th. Multiply those two, divide 50 by it. Oh, I got 10 to the 17th this time. Oh, is that what you got when you got a different exponent than me?
Oh, I got 10 as the exponent.
Ooh. Well, that's not helpful. Gosh, we're sucking. It is 8.85 times 10 to the negative 12th. Yeah, I remember that. Okay, got that right. Let's do 100 again. I'm going to take 100 squared, divide that, multiply that, divide that. I got 14 again. So I've got 3 times I've gotten 14 and one time with a student. So I'm going to assume that's correct, but just keep an eye on it. So I'll call this part B. And that looks about the same order of magnitude as the book did when it got its version of it. So we'll assume that's right. You might find that you made a mistake. The 100 is not supposed to be squared, but remember the 100 for the square centimeters. But remember, when you convert it, you have to square that. So that would account for a factor of 10 to the 4th.
Yeah, the area ended up getting moved to the numerator by mistake.
I got you. Yeah, okay. Yeah, that'd do it. Good deal. Okay, so now part C was determine the magnetic field induced. Well, what we have for part C is basically an application of Ampere's law, which is the closed integral of B dot dl is equal to mu 0 I enclosed, but it also has that mu 0 epsilon 0 d phi E over dt. So this part is now 0 because we don't have any current running. So we're really just looking for this part. The left-hand side, closed integral of B dot dl. Anybody want to guess what that's going to be? So we're going to more or less pretend this is, say, a circular plate just for ease, capacitor instead of a square plate. And basically, we're going to integrate along a path inside of that for R smaller than the capacitor. And what we're going to get is 2 pi R times B of R. In other words, we're making a hypothesis that B of R is in the theta hat direction, that sort of thing. And what we're looking at is here's the parallel plate capacitor, or one part of it. Let's say it's got a uniform magnetic field. And what we're doing now is we're realizing as this as this current starts to go down, it's going to try to create a magnetic field that goes in this way. So we're going to integrate along that direction. I'll call this my x-axis. I'll call this my y-axis. And then I'm integrating that way. So I got 2 pi r times b of r for that. And this is a radius r. And let's call this the radius r0, say. So the radius of the actual capacitor plate is r0. So that's the left-hand side. Then the right-hand side is equal to mu 0 epsilon 0 times d phi e, excuse me, over dt. Well, we've got dE dt, so all I really have to do is multiply that by the area, because the area is not changing. The orientation of E with respect to the area is not changing. So ultimately, I'm going to get 2 pi r b of r is equal to mu 0 epsilon 0 times pi r squared, because that's the amount enclosed, times dE over dt, which we actually got a numerical value for. So if I look at this, that tells me that B is going to be equal to, notice the pi cancels out, and that pi cancels out. This r squared cancels out with that r there. And I'm going to say B is equal to mu 0 epsilon 0 pi, or excuse me, mu 0 epsilon 0 times r over 2, because yeah, that'll be left there, and then times dE dt, which looks a lot like, I think it was example 2914. It's definitely the last example in chapter 29. I'm pretty sure it's the last. So it looks a lot like that result, and that's in the theta hat direction. And that's for r less than r0. For r greater than r0, then the left-hand side is still going to be 2 pi r b of r, but the right-hand side is going to be mu 0 epsilon 0 pi r0 squared, because remember, we're going to be calculating the flux, but only where there's electric field. The electric field is going to stop sharply there. So this will be an r0 squared dE dt, no vector symbol. So for that one, I get B is equal to mu 0 epsilon 0 r0 squared over 2r times dE dt in the theta hat direction again. And this is for r greater than or equal to r0. If you, as you see, if you look at the intervening case, when r is equal to r0, they cancel out and give you the same thing that we had here. So you might ask yourself, okay, does that give me the same as I got when I used this term in Ampere's law, right? We were using this, and we got mu 0 I over 2 pi r for the strength of the electric field using that particular surface. But now that we did this one, we got this crazy thing. Does that bear any resemblance whatsoever to the same electric field we got before? Well, it turns out you can calculate it this way. So this is our check, if you will, to make sure that the laws of physics are consistent. We would hate, for instance, one version of Ampere's law to give you a different answer than the other version of Ampere's law. And it turns out if you take B, which equals mu 0 epsilon 0 r0 squared over 2r times dE dt, and then you recognize that E, so I want to break this off a little bit like this so we can see, E is equal to, of course, Q over epsilon 0a. And we also know that dE dt is actually related to I by dE dt is equal to I over epsilon 0A. Well, I don't know why I said epsilon 0, epsilon 0A like that. If we plug all this back in, then we can say it's going to be this, which equals mu 0 epsilon 0 R0 squared over 2R times I over epsilon 0 pi R0 squared, which, check that out, this cancels out, this cancels out, and I get mu 0 I over 2 pi R, which is just a beautiful check. Everybody understand what I did there and why I did it? So yeah, whether we used in Ampere's law, whether we use this term, which would have been what was created by the current in this part over here, or use this term, which is what we created by the current, by the quote unquote changing electric field, changing electric flux over here, we got the same answer for both cases, namely B equals mu 0 I over 2 pi R. And that's a check mark, by the way, not a V or anything. Any questions on that? Maybe I'll make this blue look a little more obvious to be a check mark. All right, so that's one of the big things I wanted to do with chapter 31 is just correct Ampere's law so that I can actually give you Maxwell's equations in their general form. Now that we've done that, I can go ahead and state what they are, and then we can make some use of them. So there's one more law we haven't done, and it's sort of called Gauss's law for the magnetic field. So we already had the closed integral of E dot dA equals Q over epsilon naught. Notice I didn't write the enclosed because I'm trying to write it a little more succinctly. Well, it turns out if you study what this means is a particular point charge acts as a source of electric field. If it's a positive charge, it acts as a sink of electric field if it's a negative charge. In other words, it's like a drain when there's a negative charge where you got all this flow coming in radially inward towards a negative point charge. And if it's a positive charge, it looks like sort of a drain again in a sink, but this time the sink is filling up from below and you've got all this current coming out, or electric field coming out this way. Well, we never see that in reality with a magnetic field. We never, ever see a lone north pole that could push magnetic fields out, or a lone south pole that could suck magnetic fields in, and they're called magnetic monopoles. Since we don't see that, it turns out that B dot dA for a magnetic field instead of electric field is just 0. So these are both Gauss's laws, if you will, for the electric and magnetic field. That's Gauss's law for the magnetic field. That's Gauss's law for the electric field. And like I said, there is a differential form one where you can use differential equations to decide it, and that's good too. So those are the two. The electric flux and magnetic flux equations, because they're flux through a closed surface. And in fact, what I told you about Stokes theorem, which is, like I said, it's sort of like a generalized Green's theorem or something like that. You can calculate the amount of stuff leaving the surface, and that's exactly equal to the change of the volume in the surface. So if I integrated E dot dA over a surface and found that it's changing, then that change should be exactly equal to how much is leaving the surface. So you end up getting, in this case, it's a del dot E. They usually use a D instead of a D as in dog instead of an E, because that allows for an electric field in a material. But either way, the differential equation for this one would become del dot E. And now the other one, is Faraday's law. And with Faraday's law, we have the closed integral at E at dl. So this is the electric field around a loop, which is really what creates a current. That can be created by a changing magnetic field according to d phi b over dt. Okay, and remember that's Lenz's law, which says basically, hey, a changing flux is going to create a current. It's going to create an EMF, in fact, and that's what this is. This is the EMF over the whole circuit, and therefore is what's responsible for the current that the EMF created. That is going to be in such a direction that it opposes the change in flux. So remember, Lenz's law is it opposing the change in flux, and we can sort of think of that as the negative. Well, that means that a changing magnetic field can create a current. And then we have another version, which is now Ampere's law. So this is Faraday's. And this is Ampere's law with Maxwell's fix. That's the closed integral of B dot dl is equal to mu 0 I plus mu 0 epsilon 0 d phi e over dt. And that's Ampere's law. And again, that's like Ampere's with Maxwell's fix. Okay, that's it. That's the equations. These are in some sense like Newton's laws of motion, Newton's first law, Newton's second law, and Newton's third law, only they're even better than that because they actually are already correct relativistically. So in other words, when we studied special relativity, Maxwell's equations are what gave Einstein the idea of relativity because they were already telling us relativity just by its equations. For instance, when we combine these equations in a certain way, you end up getting a field, or excuse me, a wave equation that does not change from one reference frame to another, and therefore tells you that the speed in that wave equation is independent of the motion of the source or the observer. Therefore, the speed of light must be independent of the motion of the source or the observer. So that's Maxwell's equations. They're pretty cool. Like I said, they're super, super powerful. But now we can actually use that to make some sense of what electromagnetic waves are. So what I'm going to do is I'm going to imagine now. Does anybody have any questions before we go on? So what I'm going to imagine right now is I connect a battery. And what's going to happen is it's going to create a little bit of current flowing this way, right? What that means is you might actually see like a positive charge right here and a negative charge right here because the positive charges are running that way, and that's the direction we define current to be. So some lone positive charge sitting in this conductor is going to be compelled to move upward this way because it's attracted by a negative charge, and some lone positive charge inside a conductor is going to be compelled to move that way. And in fact, for that to happen, you're going to have to be creating what's an electric field. So you see right there, there's an electric field. Because as you might guess, if I take him and stick a positive charge right here, this positive charge is going to compel it to move that way. If I stuck one here, this positive charge is going to compel it to move this way, and this negative charge is going to compel it to move this way. But it's also going to have an effect where the negative charge is wanting to move it this way and the positive charge is wanting to move it this way. Those two being equally sized but opposite in direction makes it just purely horizontal there. And then over here, it's going to be like that, right? So that's the electric field near that as a result of this plus charge and this minus charge. Well, we also know that when current is flowing this way in the wire, then that's going to also create a magnetic field that, remember, stick your thumb in the direction of the current, curl your fingers around the wire, and that's the direction of the magnetic field. So you'd say, oh, well, there should be a magnetic field here going into the page, and there should be a magnetic field here going into the page, and then there should be one over here coming out of the page and one over here coming out of the page. In fact, this is going to happen on the other side too. There's electric field this way as well. Okay. Now, you can also realize that, hey, wait a second, if this is a electric field line, then in some sense you can imagine a current being created along this path, because if this was, for instance, ionized air, or if the voltage was so high that it did ionize the air, then it would compel little positive charges to follow this route. Well, that little compulsion of positive charges to move in a particular direction is in fact a way to create a current. And that current, of course, is going to cause a magnetic field as well, or excuse me, is going to cause a magnetic field as well. So you'd actually get more magnetic fields all the way around here. Okay. Now, as this current goes this way, then that little positive charge is eventually going to make it out to here, and a new positive charge will come in here. So here will be our new positive charge, and here will be our new negative charge. Here will be our old positive charge, and here will be our old negative charge. So lo and behold, what we're going to get here is another electric field going that way. So now what's happened is this electric field that was here has moved out to here. And if you wait a little while longer, it'll move out further, and we'll have sort of the same thing going on again and again and again. But if we do something a little more complicated and replace this battery with an AC power supply like this, then at one instant you'll have this plus charge here, this minus charge here. That's going to create that electric field there. And actually, you know, you can sort of see it on this side too, like that. And that's, of course, going to also cause the magnetic field here. And then the next instant, the current will be going the other way. So now we'll get this positive moving off to here. So let's do it this way. I'll draw another one. Now I've got this negative over here and this positive way the poop out there. But now I've got this negative here and this positive here. And that's creating a magnetic, or excuse me, an electric field that goes this way. But that other one's still out there going like this. And of course, the magnetic field between them is still doing the same thing as it was before, which is going this way. But then eventually that's going to run off the end. And what I'll eventually get is yet another setup. So now let's draw yet a third point in time. And now what I have is and notice this electric field is moving this way. This electric field is pointing this way because this one is this one and this one is this one. And what we have inside of here is a magnetic field perpendicular to that. And in fact, out here, and if we had done this for some period of time, we might have even had enough time to get another one out in front of it, which would make yet another turn like this. And in this case, this one would be, of course, moving upward, and then this one would be moving, or would point, I should say, downward. And that would give us, again, magnetic fields pointing this way. Now, if you got really, 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 really far away, all that would be essentially irrelevant, because really, really, really far away, all you're going to get is a electric field, let's say pointing this way, a magnetic field pointing this way, and then an electric field pointing this way, and then a magnetic field pointing this way. And these are what's called plane waves. Because if you took, for instance, a plane, let's say this way, that plane would show a constant electric field. That plane would show a constant magnetic field, all that good stuff. So when you get really far away, that's called far field. And that implies plane waves. This stuff in here is called the near field, and we don't mess with that because it's really, really ugly. Okay, now that's not to say physicists don't and electrical engineers don't. Everybody, we work with them, and in fact, if you take a more advanced course, you'll work with the near field, the far field, and the intermediate field. But the main thing is to realize that this is causing some kind of electric and magnetic field, and in fact, this turns out to be exactly what light is. So when Maxwell works out his equations, which I'm going to work for you in a second, derive for you in a second, when he gets them, there's a slot in every wave equation that tells you the velocity of the wave. Well, in that wave equation that he was able to, I see that that green's not showing up very well, so I want to make sure y'all see those words: near field and far field, plane waves. Okay, so when Maxwell looked in that slot, he did the calculation and came out that it was about the speed of light. So he realized, oh my God, this must be what light is. So the modern picture of light as a wave, at least, which when we get to quantum mechanics, everything's going to be off again. But basically the modern picture of light is, let's imagine that, let's see, this is, let's say that's my y-axis. Let's say this is my x-axis, and then of course my z-axis has to come out of the page by the right-hand rule. Okay, so what exactly is this crazy electromagnetic field, electromagnetic radiation, blah, blah, blah? Well, what it is this. Let's imagine a vertical field oscillating parallel to the y-axis, like that. What this means is the strength of the magnetic field is a maximum right here. It's smaller here, and it's in fact 0 here and 0 here. Here, the strength of the magnetic field is smaller again, but pointing downward. And here it's pointing downward, but bigger. Here it's pointing downward again, and here it's 0 again. Okay. Now that's the red. So I chose that red specifically because I was using red for the electric field above. So E is the electric field. Now I'm going to use green. Again, I know the unfortunateness of this, but if I go and choose the real directions, how this has to be, it turns out that the magnetic field will be exactly in phase with the electric field, but it'll be at a 90-degree angle to the electric field. And in fact, the electric field's the magnetic field's a maximum here. It's smaller here, but still bigger than 0. Here it's 0. Here it's 0. There's sort of its maximum. So that is actually what the electromagnetic radiation is, and the velocity of these two guys. So this is my B field. The velocity of these two guys is along this z-axis. So if you notice, E pointing up and down crossed with B, which points to the left at that particular part, gives me Z, which is the velocity direction. So E cross B points in the direction of the velocity. And that's just a fact. There's nothing we can do about it. It turns out that's always the case. Now, there's no reason to think the electric field is always going to be pointing up. In fact, we get from the sun, we get circularly polarized magnetic fields and electric fields, electromagnetic radiation. And what that means is basically at one point, you might see an electric field has this particular direction, and then the magnetic field's at this direction, but some other part in the sky, you might see the electric field pointing this way and the magnetic field pointing this way. The main thing is they're always going to be at 90-degree angles with one another. I'm going to try to make this darker so you can see it's actually in front of everything. And I'm going to try to make that red one up front. Since it's in front of that one back there, I'm going to try to make that darker. But that is what electromagnetic radiation is. And in fact, it has a lot more than the visible spectrum. In fact, the mnemonic I give my students, because I'm a big Rush Limbaugh fan, or was, he passed away recently. But anyways, I listened to him since 1988, I believe. So I use this mnemonic because he's always picking on teachers saying that we're commie pinkos and stuff like that. So I say, great excess, notice how I'm spelling excess, undermines various industries. It's actually hard to write vertically when you're used to writing horizontally. Marxism rules. Obviously, I don't believe that, but still, the point is that that is the parts of the electromagnetic spectrum. Great excess undermines various industries. Marxism rules. And in fact, this is from high frequency to low frequency, which is also from short wavelength to long wavelength, which is also from high energy to low energy. And you can also associate that with temperature. So I'll put T as well. Now, these are the parts of the electromagnetic spectrum. Anybody want to guess what this one is? Incredible Hulk. This is the help I'll give you.
Gamma rays.
Gamma rays. I broke my bottom. What's this one?
X-rays.
X-rays. I got a 10.
UV.
Ultraviolet.
Ultraviolet. I see you. I see you. So this one's
Visible light.
visible. Very good. Keeping my French fries warm.
Infrared.
Yep. Hot Pockets. Microwave. Yep. And then Bob 93.7 FM.
Radio.
Yeah. So those are the parts of the electromagnetic spectrum. The visible spectrum, in fact, is quite small. And in this order, it can't be Roy G. Biv. It has to be Vib Gior. Okay. So, and that makes sense, right? Because you expect the red to be next to infrared. You expect the violet to be next to ultraviolet. So that's really it. This, on the other hand, this red is the longest wavelength, and it's about 750 nanometers. And this violet is about 400 nanometers. That's the shortest of the visible spectrum. But here's kind of neat. You can also call this 4 times 10 to the negative 7th meters, and you call this 7.5 times 10 to the negative 7th meters. And then lo and behold, what you find out is this right here is 4 times 10 to the 14th hertz. And this is 7.5 times 10 to the 14th hertz. So you just sort of switch the abscissa, or excuse me, the mantissa of them, and you'll get the other one's frequency versus wavelength. So that's the visible parts of the spectrum. There's a really simple wave equation that we even teach in our conceptual physics and our astronomy, which are supposed to be fairly non-mathematical, and that is the velocity equals frequency times wavelength. But in fact, these are all what we call electromagnetic radiation. And what that means is they all travel at the same speed. So we'd say C is equal to F times lambda, and C is the speed of light, which I'll write right here. Now, Galileo tried to measure this, and he concluded that it was very fast. And then some other people tried to measure it, and they concluded it was very fast, but finite. And then finally, Romer, I think in 1904, roughly, finally figured out what it was. And since then, we've now defined it to be 299,792,458 meters per second exactly. That means, for instance, that 1 second is defined to be the time it takes for light to move 1 over 299,792,458 of a meter. Okay. So your book has some problems where it'll say, here's a radio station, FM 93.7, say. Well, what you have to realize is that FM 93.7 means 93.7 megahertz. So that's 93.7 times 10 to the 6. And that AM, like 850, means it's 850 kilohertz. So that's 850 times 10 to the third. So if you need to calculate that stuff, you've got to know that megahertz is what the FM dial is measured in, and kilohertz is what the AM dial is measured in. So other than that, those problems are very, very trivial. So let me just show you something really quickly. I'm going to share my screen. Let's share it with this one. Okay, so this is kind of neat. Yeah, y'all are seeing that, right? Okay, gotcha. So here's a breakdown of all the frequencies and wavelengths. And this is actually what they mean. So for instance, back when I was a kid, we had television, and it actually had a knob to change the channels. And the knob would have channel 2, which was PBS, channel 4, which was PBS, channel 3, which was CBS, as in where I watched Carolina win this weekend. And channel 10 was Wavy TV 10. And channel 13 was basically channel 13 or ABC that we have now. But then there was this place right between the two and like I think it went up to like 18 or 20 or something like that. And then there's a space right in the middle between the 2 and the 20 or whatever it was. And when you turned it on there, you went to another knob and you could move that. And there you found like channel 15, channel 33, channel 27, which was basically ultimately to become the place where I found The Simpsons, Fox, and then it became the WB and stuff like that. So what we were dealing with was the ultra high frequency, the UHF TV, was that 15, 33, and 27, and very high frequency was basically the channels 3, 10, 4, 2, and 13. And you can see also, if you look at your book, they'll have a electromagnetic spectrum, and it'll show you where the cable bands are. It even talks about in your book where the Bluetooth and Wi-Fi bands are, where your cell phone bands are, so on and so forth. A typical antenna, for instance, design that's often used is either half wavelength or quarter wavelength. And what that means is if you look at the length of the antenna and you divide it by 2 or divide it by 4, depending on what type of antenna it is, you'll get the wavelength of the radiation they're talking about. So for instance, if you calculate the wavelength for a cell phone, you'll find that it's probably 880 megahertz. And we, of course, now know about 5G, so you know we're dealing with 5 gigahertz. Now, here's the weird thing. Let me go ahead and kill this part. I want to stop sharing now. So the weird part about 5G is, why the heck does G matter? Or why does the hertz matter, right? Well, it turns out the more hertz that you turn it at, that means it's a super high frequency. So gigahertz means 10 to the 9th or a billion hertz. That means there's literally a billion signals every second. So here's the deal. You've got to take that signal, that radio signal, that microwave signal, that radio frequency signal, whatever it is, you've got to modulate it to carry some signal. So for instance, if you're listening to the FM band of your radio, they have something called frequency modulated. Your book has a picture of it, but basically you take the waves like this for, say, channel 93.7, that's 93.7 megahertz, and it has waves that look like this, but they actually take the sound and multiply that times the frequency. So some of the little lines that are like this get squished together at the intense sound parts and then stretched apart for the less intense sound parts. That's frequency modulation. Other ones, like on the AM band, they'll actually take and modulate the amplitude. So the wave, instead of being always plus or minus 1, unit or something, will actually vary depending on the modulation. Or depending on whatever signal you're putting in there. So that's how they carry it. And TV, for instance, actually has 2 of them. Stereo actually has 2 bands as well. For instance, if you're listening to FM, in case you don't have a stereo system, they have a second signal that's at 19,000 hertz. It goes up to about 15,000 hertz is the radio signals that you can pick up from sound, but the human ear can hear from 20 hertz to 20,000 hertz. The radio band only goes up to about 15,000 hertz, and then they've got another 19,000 hertz that carries basically the left plus the right. In other words, the left speaker sound plus the right speaker sound, and then the other one carries the left minus the right. So if you actually have a stereo system that can pick up left and right, all it has to do is add those 2, and you get left and right separated. If it's a system that doesn't have stereo, it's mono, then it only has to listen to the 19 hertz one. So, to the 19 hertz one. So that's how some of that stuff works. But that's all pretty cool. The big thing is, though, that the wave equation, which I was going to derive, but it looks like I might not have enough time. Let's see what I can do. So if you look at light as it's traveling and what we now know of as it is a wave, basically, I'll do this real quick. Let's see. We'll have a wave like this. And let's say this wave is traveling in the X direction, and this is going to be our electric field. Okay. It's pointing, in fact, in the Y direction. So first off, you need to know what the equation for plane waves are. So I'm going to give you that. And basically, this would say that the electric field is equal to E0 J hat, because it's in the J direction, times the sine of kx minus omega t. If it's kx plus omega t, it's going to the left. This is going to the right. Okay. Now, what that means is along any position x, you get a fixed amount. Like if I go to this x, I get this fixed amount of E. And as long as I stay at that x, or if I stay at that particular part of the wave, then it'll always look the same. Otherwise, I'll see it slowly go through these parts as times go forward. Now, we also have a, found that the green sucks, so I won't do that. We also have a magnetic field that goes like this. And notice E cross B shows me going that way, okay? So this is the magnetic field. And this, of course, would be in the Z-axis direction. So this would be B0. Okay. And that one, of course, would be E0. So this plane wave would be given by B is equal to K hat B0 sine KX minus omega t, and K is defined to be 2 pi over lambda, and omega is defined to be 2 pi times the frequency. Okay. Now what your book does is kind of a neat little derivation. You can look on my YouTube channel for what I say is a slightly better derivation, because it's just using the vector equations themselves. But you can say, let's take a little box like this, and let's say we're going to integrate around that. Specifically, we're going to integrate around that and use Ampere's law, and also use Faraday's law. So first off, what we're going to do is we're going to imagine us going around this area right here in this direction. And we're going to use Faraday's law. The closed integral at E dot dl is equal to negative d phi b over dt. And you see the magnetic field, of course, is pointing perpendicular to that. So things are really nice. Well, that actually gives you what you need. Oh, and by the way, you can combine this and see that F times lambda, which I already showed you, C equals F times lambda. F times lambda is actually the same thing as omega over K, which turns out to be the velocity. So that's something else that comes from this if you want to do it. This side right here, though, we're going to say this height right here is, let's say this height is delta y. And let's say this height right here, or this width, is dx. Okay. And notice the E is only parallel and anti-parallel to it on these sides. So this left-hand side is only going to matter on the left and the right. In other words, it's going to be 0 down here, and it's going to be 0 up here, because the dot product's going to give you 0. So in this case, the electric field is actually going up, and I'm going to say that is actually equal to E plus DE. In other words, this is where E is defined. I go ahead by DE. So I'm going to say E plus DE times delta Y minus, this one's going the opposite direction, so I got a minus, and that's just going to be plain E times delta Y. That's the left-hand side. But the right-hand side is going to be my magnetic field, and that's going to be basically the flux of it. So the flux is the magnetic field times the area. So I can say right-hand side, or at least part of the right-hand side, negative d phi b over dt. Well, in this case, we're going to say the d phi b is really just dB. And it's going to be dB. Now I've got to take that and multiply it by delta x, or excuse me, by dx. That gives me the width of the area, and then times delta y, which gives me the height. And of course, now I'm going to divide all that by dt. So I can reduce this. You'll see that E delta y minus E delta y cancels out. So this left-hand side just becomes dE times delta y. And this part right here becomes negative dB, oh, I left off the negative dB dt times dx delta y. I set them equal, I get dE delta y is equal to negative dB dt dx delta y. That's got to be true for any delta y. So that gives me sort of dE over dx is equal to negative dB over dt. But in reality, E and B are both functions of position and time, so I can't really use these plane derivatives. In fact, I'm supposed to use the partial derivatives, which partial derivative with respect to x is equal to the negative partial derivative of B with respect to t. Now I can do the same thing with a little box down here. again, making that delta x or that dx down here, but making this, in this case, delta z. And again, when I do that, I'm going to have to choose which direction to go around. So I'm going to go around this way. So this one's a positive and this one's a negative. And the reason I'm doing this is because I see as time goes by, this thing's moving this way. So the magnetic field is actually decreasing, and I want it to be consistent with that direction. So when I do that side, I end up getting basically closed integral. Now I'm doing Ampere's law instead of Gauss's law. I mean, instead of Faraday's law. So this is left-hand side. This time I get B times delta. Oops, paper just fell, crap. This time I get B times delta X, or excuse me, delta Z minus B plus dB, because I've moved over to this part, times delta Z. The B and the minus B delta Z drops out, and I just get negative dB delta Z. The right-hand side, which remember from Ampere's law, we're not picturing any current, so I'll leave that term off. I get mu 0 epsilon 0 d phi E over dt. So for this right-hand side, you can check it for yourself if you like. It's pretty straightforward. I'm just going to get mu 0 epsilon 0 d phi E over dt, which you can see is mu 0 epsilon 0. And then we're going to have dE dt. And then, of course, it's times dx and delta z. So we set these two equal to each other. We get negative dB delta z is equal to mu 0 epsilon 0 times dE dt dz delta z, or excuse me, dx delta z. Again, this is true for any delta z. So we end up getting the partial of b with respect to x is equal to the negative of mu 0 epsilon 0 partial of e with respect to t, for the same reasons we did before. So those are sort of wave equations. They're not second order like we're used to, but in principle, all you have to do now is you could take the derivative of this with respect to time, and you could change the order of it. So we'd say the partial with respect to x of not b, but the partial of b with respect to t would be the partial with respect to x of negative dE dx, like that. So I just use that equation there. So this is now the negative second partial of e with respect to x. Oh, that was supposed to be t, by the way. With respect to x, with respect to t, gives me basically the partial, the other side, which is the partial of e with b with respect to t. So I could actually mix it that way. It's kind of messy, and you can play with it a little bit. But if you look on page 822, you'll get you'll see how you can do that. But what we can do is now take these electric field and magnetic field plane waves, put those in, and what we'll find out is that we get the second partial. So here's the final result. When I combine this equation and this equation, I get the second partial of b with respect to time squared is equal to, oops, I was just looking on the wrong page of my notes. Why did I even do that? Oh yeah, I didn't want that, sorry. When I plug in this in here, you can see that the partial of e with respect to x is just going to be k times E0. So we end up getting, in one case, we get E0 over B0 is just equal to omega over k, which we know is velocity. In general, E over b should equal the velocity, which is going to be the speed of light. We just know that's the case, right? Then we can take the other one and we get b0 over e0 is actually equal to mu0 epsilon 0 omega over k, which you can see is mu0 epsilon 0 times v. So if you solve for v, we know v is equal to c. That turns out to be 1 over the square root of epsilon 0 mu 0. That was the big discovery. Okay, if you actually put 8.85 times 10 to the negative 12th and then multiply that by 4 pi times 10 to the negative 7th, take the square root and flip it over, you will get 299,792,458. Of course, you're not going to get exactly that because we don't have that many sig figs for epsilon 0 mu 0, at least not in the values I've given you in class. Okay, the 4 pi times 10 to the 7th, that goes any number, but the epsilon 0, I think in the front cover of your book, you might get 6 sig figs, but definitely not 9. So that's it. So you now know what you need to know to be able to do stuff. The only thing that's left is something called the Poynting vector, which the Poynting vector is the energy per unit time per unit area, and it's E cross B. Notice E cross B points in the direction of velocity. And the other thing is the pressure, and that's generally 2S over C is the radiation pressure that you get, where S is an average. So those equations you just need to know how to apply for simple problems like you see in the examples, and we're done. Class was supposed to be over at 6:05. I got over about 6:06. I'll wait for the last person to leave in case anybody has any questions. Don't forget to look at your due dates on your homework. You got some homeworks coming due. Make sure you get them. Thanks for coming, everybody.
I had a question,
Go for
Professor
it.
Dr. Younger. So are the homeworks? Yeah, so someone asked in chat, that was my question. Are you going to change the homework dates? Because I checked, it's both of them are due tomorrow, or are they supposed to be due tomorrow?
Did you just check them? You mean for chapter 31 or chapter 30?
For chapter 30.
Yeah, chapter 30 was supposed to be tomorrow and the next day. I think I've got to, I think I might have made it to Wednesday is what I thought. Let me pull that up real quick. Chapter 30 we finished last week. That's why I didn't have a problem with that. But let me go ahead and change it anyways, just to make it a little easier on you guys. I'll be nice. All right, I'm pulling it up right now. It might take a few seconds.
Yeah, I was just confused because in the beginning, I checked in the beginning of class and you said something about the dates, and I don't know if you were going to like change it then already, or if it's already good. I don't know like what the original plan was.
Gotcha. Yeah, so next we're supposed to cover, now that we've covered chapter 31, we're going to go into thermodynamics, but what I'm looking at right here is chapter 30. Let me see, chapter 30 conceptual is due 3/29. Yeah, I'm okay with that one. I'll leave that one, but I want to make sure the chapter 30 problems are due a little later at least. So let's look for that. Chapter 30. Oh, there's part 1 and part 2. I'm going to move that. I'll move that to, I think I'll move that to Friday. No, I'll do it Saturday. That way I'll give you a little bit more time. So I'm going to make it do, what the hell, I'll do it Sunday. No, I'll do it Saturday. I don't want it to give you so much crap that you can't do anything. Whoa, Nelly, I just did something bad there. Hold on a second.
So like, because I'm just worried, like if we push back chapter 30, part 1 and part 2, then will it like, how will it affect chapter 31?
Yeah, that's why I didn't want to push it too far back. So what I did was I pushed chapter 30 conceptual is still due tomorrow, but chapter 30 part 1 and part 2 are now due on 4/2, which is Saturday night at 11:59, and chapter 31 is due on 4/5.
Okay.
Which is Tuesday of next week.
All right.
Let me see 31. Yeah, and conceptual for 31 is due on 4/3. So yeah, I think that's a little better for you.
Yeah, I plan on doing like try and finish it just like because usually we have like, I'm gonna try and finish it by Tuesday, because usually we have like a week between like every conceptual and homework. So I don't have to like do everything in like a few days, and like, because I'm gonna have more work if I just wait until.
Exactly. It's better to do a couple every day. And plus it's better to just, look at it every day. Just from a learning standpoint, you get more out of it if you're looking at it every day, as opposed to taking a week off or 5 days off or whatever. So that's cool. Well, I should have this video posted tonight and the actual notes as well.
All right. Thank you, Professor.
No problem. Have a good one.
Yeah. Have a good one.
Edmium, did you have a question, or James?
I do. I had emailed you last week, but I just realized that I had accidentally my computer auto-filled the email send with midterm.
Oh gosh. Yeah, I might not.
Yeah, I was gonna ask if I could have a few extra days on at least the next 2 chapters of homework, since I sprained my wrist pretty bad.
Yeah, I tell you what, when you're done with them, I'll give you, let's say, an extra 7 days. So when you're done with them, email me and I'll set it back so you get another 7 days.
Okay. Thank you so much, sir. You have a wonderful evening.
You too. Anybody else? All right. See you, folks.